Alright, gentlemen, I apologize for the other video. There was no sound. So just going through this a little quickly. Exponential functions and logarithmic functions are inverses. We know that exponential and logarithmic functions are inverses because when we saw a number raised to the log where that base matched that number, they canceled out. So that's how we know that they're inverses. It's similar to the idea of having like 3 times x equals 18. We want to undo that. And that's multiplication, so we undo that by dividing both sides by 3, right? That's a product, 3 times x. We undo that by dividing, right? So multiplication and division are inverse operations, kind of the same idea, right? And this box just kind of goes through that description. If you have two exponential functions that equal the same thing and they have the same base, they must have the same power. And the same idea with logs. Two logs that equal the same thing with the same base, they must have the same thing inside. Alright, and now just a couple rules. If we have the same base, we can cancel out the bases and just work with the exponents. Okay, and we'll kind of see why down below. If we do not have the same base, we have to take the log of both sides and then we solve for x. Remember, you want the base to be what the base of the log is. If we have base e, we use ln and then solve for x. Right, so kind of the same idea. The log base, you want to match the base of the exponent, and that's why we use ln with e. All right, let's do this one. First, we see that this base and this base match. So we know right away we could technically just write this as x plus 4 is equal to 2x minus 1. Now, how does that happen? Okay, and we need to know how it happens because we're going to do it again later when we don't have the bases match. So we could just write it like this and we would solve and get 5. But let's see here. This base is 3, this base is 3. So what you could do is, well, let's say we take the log of both sides, just like it says if the bases weren't the same. Take the log of both sides. Now, we want to make sure when we take the log of both sides, we don't want to just do log and not put a base here, because if not, that means we're doing it with 10. That's not going to benefit us. So we want this number right here, the base of that log, to match this number. We want them to match. So we know this has to be a 3. Why? Because the log base 3 here and this 3, they're going to be able to turn into 1. So we do this log base 3 to both sides. Got to do the same to both things because we choose this number, the base of the log, to match the base of the exponent because they're going to be able to turn into 1. So what do we do next? Well, we know our properties of exponents that we saw yesterday. You can take the power and put it out in front as a product. So this really is x plus 4 times log base 3 of 3 is equal to 2x minus 1 times log base 3 of 3. So we see the exponent comes out in front because that's the properties of logs. The exponent comes out in front, that's the properties of logs. We chose this 3 to match this 3. It also matches here, and we do that because log base 3 of 3, that's just 1. So I just get exactly what I had. X plus 4 is equal to 2x minus 1. Now we don't have to show these steps every single time when the bases are the same, but when they're not the same, we're going to have to show those steps. Okay, and as we said, a very simple way to solve this, you get 5, right? It's a very simple solution after you do the logarithmic work in the beginning. Okay, so let's see another one. Number 2. Okay. I want to get this exponent thing by itself. It's not. It's multiplying a 6 in front. So let me do the inverse operation and divide both sides by 6. Now I get a 4 and an 8. So we see here this 4 and this 8. Right? They're not the same base, so I can't do anything. But what do I notice about this 4? This 4 and this 8. They both essentially have inside them, this is a 2 squared, so I could do something with that. This is a 2 to the third, so I can recognize them that I can make this 4 and this 8 become the same base. Right? My x minus 1 still stays there. It's still there. I'm changing the 4 to a 2 squared. I'm changing the 8 to a 2 to the third, and here's the x minus 1 still there. We know by our properties of exponents that we have to multiply, so it's really 2 to the 2x minus 2 is equal to 2 to the third. All right, so now I've recreated it so that they do have the exact same base. I can just skip right to the part where I set the exponents, the powers together, and I get 2x is equal to 5, and x is equal to 5 over 2. Right, so very simple solution. So once we recognize that we have the same bases, we can just set the powers equal to each other. And we know we have the same bases because I was able to change the 4 into a 2 squared and change the 8 into a 2 to the third. Right, so nice simple equation right here. Right, so if we have the same base, very simple. If we don't have the same base, can we make it have the same base? Okay, let's look at this one. 5 to the 2x minus 1 equals 20. Add 1 to both sides, because I want this power to be by itself. 5 to the 2x is equal to 21. So I got this exponential by itself by moving the 1 over. All right, this 5 and this 21, not the same base. Can I make this 5 and this 21 become the same base? No, because 5 squared is 25, so I can't make them match. I got to take the log of both sides. All right, so we got to do the log and the log of both sides. The right-hand side is very easy, log of 21. Okay, and the left-hand side, log of 2x, log of 5 to the 2x. Okay, now how do I pick the base of the log? Well, I want the base of the log to match my exponential's base. So I need this to be a 5, and I got to do the same to this side. So this is a 5. Log base 5 of 5, I'm choosing that so that these two match. I just do the same to this side. I'm basing it off here because this is the one with an exponent. Just as we saw before, the 2x comes out in front by our properties of logarithms. Log base 5 of 5 is equal to log base 5 of 21. Okay, and we saw just as last time, log base 5 of 5, that's 1. 2x is equal to log base 5 of 21. All right, so since this turned into 1 right here, this turned into 1. Here's my 2x. I'm solving for x. Divide both sides by 2, and I get x is log base 5 of 21 is equal to 2. And that's just some number, right? We never really did anything with the log base 5 of 21 because that's just a number we would type into our calculator. Okay, and then we divided both sides by 2, so this is just some number we have. Okay, let's look at number 4. So now we see this one where our base is now an e. I have exponent stuff alone. I have a 29, so obviously I can't make them match. And I don't have to move anything over. So let's just take the natural log of both sides. We use natural log because my base is e. Here's my 29 inside. Here's my e to the 2x minus 5. Okay, again, our same properties of exponents, of logarithms. The exponent comes out in front, 2x minus 5, times ln of e is equal to the natural log, the ln of 29. Okay, now we know that the natural log of e turns into just 1, and I have 2x minus 5 is equal to the natural log of 29. Simple to solve from here, add 5 to both sides. The natural log of 29 plus 5. Okay, and again, make sure we do not put the 5 inside the natural log. The only thing that was natural logged was the 29. We already dealt with the 5 over here in the log, so we don't add the 5 into the log. Be careful not to do that. Divide both sides by 2, and x is equal to the natural log of 29. That answer plus 5, and then the whole thing divided by 2. Right, and just like when we had with radicals where you can't add to within a radical. Same thing, where you cannot add within the natural log. Okay, let's look at number 5. We'll do this one a little bit quicker because it's a little bit more of the same, but again, I do not have the log by, or the exponent by itself, so I divide by 2. We're always working to get it by itself. Okay, so I got it by itself. Here's the only exponent thing. This 3 I cannot make into a 6 by any power, right? 3 squared is not 6, it's 9. 3 times 2 gives me 6, but I don't need that. I want it to be with powers, with exponents. So what do? I got to take the log of both sides because I can't get them to match. Log of both sides. Here's my 6, here's my 3 to the x minus 5. We choose our base here to match that 3. This 3 matches that 3. I can kind of skip the step here. I know what happens. The x minus 5 comes out in front. This log base 3 of 3 goes to 1. So I can kind of skip that step and just go right to here. I add 5 to both sides. Again, I do not put the 5 into the log. I leave it on the outside. And there's my answer. Okay, let's look at number 6. This is probably the hardest one we will see. The hardest one we will see. Okay, so we do have 2 bases that are not the same. And I cannot make a 3 become a 5, so I have to take the log of both sides. Now, what do I choose, base 3 or base 5? You could choose either one. It does not matter, because you want to choose one of them so that they cancel, but it doesn't really matter which one you choose. I'll just choose a 3 so that I get the left-hand side, this to become a 1, but it doesn't matter. You would have to choose one of them. Okay, so here's my 3, x plus 4. Here's my 5, x plus 6 to the x plus 6. This base I have to choose. I'm going to choose it so it matches with the 3. I have to do the same to the other side. I have to keep, just so that I stay equal, I have to use the same log to both sides. Nice thing on the left, we know I'm just going to get an x plus 4. I'll write down the log 3 of 3, but I know that's going to cancel out and be a 1. Now this side I got to do it out. So here's my x plus 6. It goes out in front, just as we saw on the other side. Log base 3 of 5. Okay, we know this becomes 1, and we just have x plus 4. Nice and easy on the left-hand side. The right-hand side, not so much. This whole thing does not simplify, so now it's a number, some number, multiplying by this sum in parentheses. So just like when we had inverses, you have to distribute into that parentheses, right? Distributive property. If this were a number like a 2, you would distribute in on the other side. Same thing, log base 3 of 5 is just a number. So let's write out what we get. So we get x log base 3 of 5 times, or plus 6 times log base 3 of 5. Right? And we're just holding around this log base 3 of 5 the whole time. It's a number, it's just some weird looking number, but we just carry it through. Very similar to inverses here. This, we want to move to this side because you want the x's together. We want to solve for x. We want this and this to be on the same side. And we want this and this to be on the same side. So I'm going to take this x, move it over here, and I'm going to take this 4 and move it over there. All right, so just like when we were solving inverse equations, you flip the x and the y and you have to solve for x, same idea. Log base 3 of 5, right? So I subtracted to bring it over here. I get equals 6 log base 3 of 5, and now I have a minus 4. Here's my minus 4 brought over. Okay, exactly like inverses, I have 2 x's here, very similar to if I were to have something like 3, or I'll do like x minus 3x. You can view this as, well, it's really 1 minus 3 of x, so you get a negative 2x. Right? So very similar, same idea, x minus 3x, right? If you almost like view it as a GCF, like what is the coefficient here? The coefficient is a 1 minus a 3, there it is. I have 2 x's, so I write it as 1x, and I subtract these 2, I get negative 2. Same thing happens here, except I cannot subtract them because it's 1, the coefficient of this, minus, this is my coefficient on the wrong side. Almost like you're doing a GCF. Okay, and I have my 6 log base 3 of 5 minus 4. That stays the same over there. Now that I have my x by itself, I can divide both sides by that, and I get 1 minus log base 3 of 5. And here is my answer for x. This right here is my answer for x. Okay, so this big convoluted mess, but we have log base 3 of 5 throughout. If I would have done this in the beginning, made this a 5, this side would kind of cancel out. I'd have an x plus 6 floating around, and over here I'd have log base 5 of 3 all throughout. It's the same decimal representation, it just looks a little different. Okay, again, so that's the hardest one. Very similar to what we did when we did inverses. You get your x's combined, you do the same kind of a procedure. Okay, let's look at this one. I do not have my exponential stuff by itself, so what do I have to do? Move my 7 over. Add 7 to both sides. E to the 4x minus 3. E to the x minus 2 equals 10. All right. Now, normally when I have a fraction and an equal sign, I have to cross multiply. This is not the case, however, because I have the same bases, just like when we saw something like x to the 10 over x to the 8th. You could say, oh, well, that's x squared. Same idea. You subtract the powers if you have the same bases. So 4x minus 3 minus x minus 2 is equal to 10. I can simplify that top a little bit. 4x minus 3 minus x minus 2. 4x minus x is 3x. Negative 3x minus negative 2 is minus 1. Nice simple equation. So a little bit of manipulating to start, and we get it to be much simpler. Again, recognizing our bases are the same here. Now these two obviously are not the same. It's an e, so I have to take the ln of both sides. Take the natural log of both sides. I know what's going to happen on my left-hand side. I'm just going to have a 3x minus 1 because my natural log and e are going to cancel after I bring the 3x minus 1 in front. And this natural log of 10 just stays there. That's just a number. Add 1 to both sides. And I get plus 1. And then I have x is equal to natural log of 10 plus 1 all divided by 3. Okay? So there's all our work with when we have exponentials. You want to take the log or the natural log of both sides such that your base of your log matches the base of the exponent. And in this case, the ln and the e are the ones that match. When we do it the other way around, right, we do kind of the opposite, where we change it to the exponential form. We change the equation to be the exponential form. We want the bases to match. Regular log is base 10. Log base 3, obviously that's base 3. Here's my ln and there's my e. So it's the same idea, just we're kind of working backwards. Okay, so looking at this one. This base, although we can't see it, it just says log, so we know this base is a 10. Right? And what we're going to do is basically take this and make that the power of the 10. So I use this 10 because the base of this log is a 10. So I put a 10 here. This whole thing becomes the exponent. And I do the same to the other side. So here's my 10. Here's my 10. I'm kind of like reversing it, where I'm making it have the same base. Here's my 10. Here's my 10. I choose this 10 because this log's base is 10. I know that these two right here are going to become 1, which means I get x squared is equal to 10 squared. So clearly we can see x is equal to 10. Okay, let's do another one, a little bit weird. See here, ln. There's no base there because the base is e. What do I do with that e? Well, I make that the base of what's written up there. So ln is the base of this, or e is the base of this. So I put my e there, and I'm making this the exponent of the base e. When I do that, this is able to cancel and turn into 1. So I get x squared is equal to e to the third. How do I solve from here? Square root both sides, square root of e to the third, or you can say e to the 3 over 2. They're the same thing. Okay, looking at this one again. ln, ln. They're the same, but I got to raise both of these to the e. It's very nice. I get the same thing on both sides, so I can go make e my base, and I'm choosing that because it'll cancel out with the ln. This becomes 1, this becomes 1, and I get 4x minus 7 is equal to x plus 5, right? We're choosing that base so that it cancels out with my log, so then I just have to deal with the exponents, right? You're essentially making an exponential equation. And I get here, very simple, minus x, 3x minus 7 is equal to 5, plus 7, 3x is equal to 12, x is equal to 4. Nice simple equation for there. Okay, just two more, and then we're done. Log base 2 here. Okay, so now I know I got to use 2 as my base. 2 is my base. Okay, this becomes the exponent. There it is. And this becomes the exponent. I'm choosing 2 because I want the base to match the base of my log. This 2 matches with this 2. I choose that because these will cancel, leaving me with a 1. So I get 5x minus 17 is equal to 2 to the third. Right, since we did the same thing to both sides of the equations, 5x minus 17 is equal to 8. They stay equal. Plus 17, 5x is equal to 25. X is equal to 5. Okay, right? So we're always choosing what to raise it to in order to get the log to cancel. So exactly the opposite of what we had before. When we saw a log and we used the base, right? Same thing up here. When we saw an exponent, a 3, we matched the base of the log to that 3. We're doing the exact same thing, just the opposite. We see the 2, we're matching that 2. Let's just do this last one. Again, as we saw before, you want to get the natural log by itself. Subtract 3 from both sides. 4 natural log of 2x minus 1 is equal to 8. Just like if you were solving for x, you want to make this by itself, and then we can redo our evaluation. Divides both sides by 4. The natural log of 2x minus 1 is equal to 2. Okay, natural log means we have to take e and make e what we're raising, what our base. And we're going to raise the e's to what we had written up above. We choose e because it matches with the ln. Here's my power of the e. Here's my power of the e. They cancel right here to become 1. And I get 2x minus 1 is equal to e squared. Nice simple solution from here. E squared plus 1. X is equal to e squared plus 1 all over 2. And there's all of our work. Sorry about the lack of sound in the first video. I hope this is helpful. And again, your answer key will be released for the classwork prior to you being able to do your homework. Okay, good luck.